Hi, this is the outline video for the final chapter of business decision models, which is Markov chains. This chapter begins with building a foundation by explaining stochastic processes, then introduce Markov property and Markov chains, and right after that, further explanations are given about the Markov chains. A stochastic process is a sequence of probabilistic events and can be defined as a family of random variables. The random variables are indexed by a set of numbers, usually viewed as points in time. Representation of a stochastic process, as you can see here in the middle, it is an index collection of random variables. An index denoted by T in general is a member of an index set uppercase T. T can be hours, days, etc. and uppercase T can be a set of the same measure of time. The values of xt are called the states. The set of all possible values of the states comprise the state space S. If the state space S has finite number of members with a distinct value, then the process is called discrete state process and often referred as a chain. A stochastic process has the Markov property if the probability of the future states only depends on the present state, not on the sequence of the events of the past. A chain is a process that moves from a state to another by some probability law. Therefore, a Markov chain is a stochastic model describing a sequence of possible events with probabilities of each event depending solely on the previous event. Here, it's important to emphasize that Markov chain is not a decision-making process. In fact, it provides probabilistic information about the decision situation. Let me explain the Markov chains by an example. Here we have an example of weather prediction. The assumption is that the next day's weather condition is only up to the condition of the previous day. Weather can only be sunny, cloudy, and rainy. And for the states, S1 for the sunny condition, S2 for the cloudy condition, and S3 for the rainy condition. These three comprises the state space. Xt denotes the state of the weather for day T. In this model, the point of interest is the transitions from one state to another. The probabilities of moving from one state to another are called transition probabilities. Here, Pij is the one-step transition probability from Si to Sj. The sum of the one-step transition probabilities from a state to all possible states is equal to 1. That means all possible scenarios are considered by 100%. The data for our example, that is the transition probabilities, are verbally stated and written in here. This chunk of words is not easy to understand, so there is a convenient way to express the probabilities of the transitions, and these probabilities can be given in a matrix called transition probability matrix, and it is given here at the below. In this matrix, rows for the present conditions, as we mentioned, S4 for sunny day, S2 for cloudy, and S3 for rainy day. These rows are for the present conditions. And the columns are for the forthcoming conditions, the next conditions, the conditions that going to be occurred after the transition. These are the transition probabilities. And alternatively, these probabilities can be represented by a diagram, as you can see here at the right. Here the nodes are the states and the arcs are the transition probabilities. Let's explore the probability of a sunny weather right after a rainy day. So we have our transition probability matrix. As we mentioned, the rows are for the present conditions, and we are looking for a sunny condition, and the columns are for the next conditions. And in this matrix, now we'll look for the probability of a sunny weather right after a rainy day. So S3 is for rainy present condition, and it is for row 3. And the sunny condition for the next day is at the first column. So now we're looking at the intersection of the third row and the first column. This element, the value of this element, gives us the probability of this transition, and it is 0.2. That means after a rainy day, the weather will be sunny by a chance of 20%. For the day after tomorrow, to find the probability of a sunny weather, we sum the multiplications of the transition probability from rainy condition to a distinctive condition and the transition probability from the distinctive condition to sunny condition. So we have here three combinations, each of which ends with a sunny condition. And all these three combinations begins with rainy conditions. So only thing differs is that the one in the middle, this condition, and these are sunny middle conditions, cloudy and rainy. In each condition, each combination, we have two transitions. As you can see here, we have three conditions and two transitions. For the first combination, the first transition is from rainy condition to sunny condition, and the second transition is from sunny condition and again to a sunny condition. And for the second combination, the transitions are from rainy to cloudy and cloudy to sunny, and for the third combination is rainy to rainy and rainy to sunny. We know the probabilities of each of these transitions by looking at these transition probability matrix. So we know the probabilities of these. However, this combination has two transitions, so it's these consecutive transitions requires combined probabilities. So we multiply these two probabilities. 20% times 80% yields 16%. For the second one, we can see a transition probability from rainy to cloudy. It is rainy for the third third row. Cloudy condition is for the x2, so we're looking at the second column. Third row and the second column, the intersection gives us the probability, which is 0.3, and it's 30% probability of the weather being cloudy right after a rainy day. Similarly, we can obtain the probabilities from the transition matrix. So for the second combination, we also multiply these probabilities and we obtain 6% of probability for the weather to be sunny for the day after tomorrow when today's condition is rainy. Similar calculations are done for the third combination. So here we have three probabilities for each conditions. Each of them ends with a sunny weather. That means this is the desired condition that we have. So we have to calculate these three. We have to sum these three probabilities. So summation of these three yields 32%. That means it is 32% likely to be the weather to be sunny for the day after tomorrow when today's condition is rainy. So this is the probability we have here. The same probability can be reached by an alternative way by calculating the transition probability matrix for all conditions at once, then by looking for the probability of desired beginning and ending condition. In our case, beginning condition was rainy and the ending condition was sunny. To obtain the transition probability matrix for the day after tomorrow, the transition probability is multiplied by itself. As you can see, this is a matrix multiplication, and it differs from a normal multiplication operation. In the matrix multiplication, we obtain this result matrix here at the right hand side of the equation. We obtain each element of this matrix by calculating separately. For instance, for the one in the final matrix, that it is on the left at the bottom in the red circle, we obtain this by multiplying the third row of the first matrix by the first column of the second matrix. So the first element of the third row in the first matrix is multiplied by the first element of the first column in the second matrix. So it is 0.2 times 0.8 plus, now we move on to the next element, plus the second element of the third row in the first matrix is multiplied by the second element at the first column in the second matrix. So it is 0.3 times 0.2 plus, now it's for the last element, the third element of the third row in the first matrix is multiplied by the last element at the first column in the second matrix, which is 0.5 times 0.2. The sum of these three gives us the value of this element. The other elements are calculated in the same with the same method. So now we have the transition probability matrix for the day after tomorrow. Now we'll look for the probability of our desired beginning and ending condition. Our beginning condition was rainy, so we're looking at S3, which is the third column, and the ending condition is for a sunny condition, and it's given in the first column. So the intersection of the third row and the first column, this is the element we're looking for, and its value is 0.32. As you can remember, this value is the same with the one we calculated in the previous slide. Similar calculations are required for the forthcoming days, such as third and the fourth day. For the Markov chains, a steady state is reached when the number of forthcoming days tends to infinity. In the steady state, probabilities converges to constants. That means in the long term, the probabilities of a transition becomes stable to values of probabilities, becomes constant, it becomes steady. I mean for the enough distance of time. In here, steady state normally achieved in when the forthcoming days tends to infinity. The states of the Markov chains can be classified by their transition probabilities. If two-way transition is possible for some states, then they are classified as the communicating classes. A state is recurrent if the transition can only be to itself. Otherwise, it's transient. For example, a transition matrix and its transition diagram are given here in the middle. For this model, there are three communicating classes. The first one has a single state and it is for state 0, and it is for the 0 states the only possible transition is to itself. So this one is only comprises a class. Similarly, state 4 is a class with a single member, as it is only can recur to itself. On the other hand, states 1, 2, and 3 comprise another class, as the transition is possible among them. So this is another class with 3 elements. Here, state 0 and state 4 are recurrent states, and state 1, 2, and 3 are transient states. This is all for this video. Please do not forget to revisit the previous chapters to be successful in the final exam. I hope you the best for your examinations. Bye.